Thank you, Bill. Thank you for inviting me. Can you hear me well? It's a privilege always for me, a privilege to talk for Auckland Astronomical Society. So let me greet you saying hello, hello astronomers. Great to have astronomers. So the pillars of cosmology, theory and observations. And actually, it's all about 100 years since great things happened. I will tell you what exactly I mean. Right, first I think I will show a few beautiful pictures I discovered recently that you probably saw them. The James Webb Space Telescopes, photos of some galaxies. And here is interesting picture. By diagonal, on the right is Hubble Space Telescope, optical wavelengths, visual light. And here is James Webb Space Telescope, so that's infrared. You know, James Webb is sensitive from 0.6 micron to 28 micron something. So basically this is dust is bright and here dust is dark. So, well, another opportunity to look at this beautiful objects. And look at that, that's a ring of star formation here. This and another one. Actually, that's probably typical. And now they say that probably star formation goes from central parts to the periphery as a ring. Okay. Oh, that's another recent picture, March 2024. That's an image of the supermassive black hole in the center of the Milky Way galaxy with the lines of magnetic field. Actually, this is picture when they use polarization data. So amazing stuff is happening. So I mentioned Hubble Space Telescope, and it managed, it can go to the redshift of approximately 11, which means look back time 13.3 billion years or 500 million years since the Big Bang, Big Bang. James Webb Telescope looks up to Z15 redshift, look back time 13.6 billion years, 200 billion years since the Big Bang. That's when we think the star formation started in the universe, maybe between 100 and 200 million years. But we can see even earlier stages of the universe. Actually, this is the photo of the whole universe made by Planck telescope, Planck mission. That photo is 2013. Well, I say photo. Normally photo means light, but this is radio waves, microwave background radiation. That's how the universe looks like. And it goes to the time when the universe was 380,000 years old. So we can get information from that time, not just 200 million years from the beginning of the Big Bang. Mulvey, the projection, that's nice projection, I remind you. The whole Earth in one projection. So here we see the whole 4 pi steradian, universe. And what we get from this, we have this information. Actually, this information tells us, it's like histogram. How many little spots have size of 1 degree? And you see that the maximum. And then there is another maximum and another maximum, another. And Planck team, they claim that they count up to 7 maxima. And there is a theory where you can take you know, the width of each, the height of each. You substitute in the equations and you solve this system of equations, and you get information about the universe. That's amazing. This is basically, these things are footprint of baryonic acoustic oscillations in the early universe. This is the photo of the universe when photons became free of matter. Before that, before 380,000 years from the Big Bang, the universe was not transparent to light. The photons couldn't leave freely, travel to us, and after this period, they travel to us with speed of light, of course, and reach us now. So we see this picture. What we learned from this graph, age, size and curvature of the universe. This is H consistent with infinite Euclidean space, flat universe, flat in terms of 3D, not 2D, flat. Contents of the universe in terms of mass energy, about 5% of atoms, well, almost all hydrogen and helium. Out of this 5%, just 0.2% in stars. The rest is gas, intergalactic media and interstellar media. Cold dark matter, mysterious dark energy, a little bit of neutrinos, a little bit of photons. This is the last data release of the Planck mission. Yeah, just to remind you where we are. So Hubble, like 500 million years, James Webb 200 million years, CMB 380,000 years since the Big Bang, earlier years. How about 3 minutes since the Big Bang? We talk about nuclear synthesis, when first complex nuclei were formed, like helium-3 isotope, helium-4, deuterium, tritium, lithium-7, and we can measure their primordial abundance and check whether our model of the Big Bang is correct or not. And it proved to be correct. I'll show you pictures later when I talk about this. Maybe earlier, look at this. This is not letter V. This is new. Sign for neutrinos, cosmic neutrino background. And there is even this, that's something that actually I am very proud. Our PhD student, Axel Rogers, is one of authors of the paper which announced discovery of discovery of gravitational wave background in the space. The announcement was just 1 year ago. So 3 facts and 1 theory. We will talk about Hubble-Lemaitre law, expansion of the universe, origin of the elements, primordial nuclear synthesis, 3 minutes since the Big Bang, cosmic microwave background radiation, that's 380,000 years photo of the universe. And theory, Einstein general relativity, universal theory of gravitation, modern universal theory of gravitation. I looked in different sources for what is cosmology, and they say about the same. Science of the origin, development of the universe, science, origin, development of the universe, concerned with entire cosmos, ultimate fate, study of large-scale properties of the universe as a whole. I like this, as a whole. Universe as a whole, yes. That's what cosmology is about. And here I like it very much. Cosmology concerned with the universe from the smallest scales to the largest. And here I show my students, actually I forgot to put it, the picture of ancient dragon called Ouroboros. It's, maybe you know, it's devouring its own tail. So the smallest affects the biggest in the universe. And people who work in elementary particle physics, they always come to cosmology and backwards. So there is this Ouroboros effect now, the smallest and the largest. From a few textbooks, Introduction to Cosmology, Science of the Universe, they talk about the same science that aims to understand origin, evolution, structure of the universe on its largest scales, but you remember that smallest scales should be included. Some history, cosmology, a very simple universe, stars, the sphere of stars, the Earth in the center, no rotation around Earth's rotational axis, the sun. So that's Aristotle Ptolemy. Ptolemy actually helped astrologists. He added epicycles. So if you have an orbit of a planet, for example, Mars, and you have a point on the orbit, I ask my students in Ptolemy model, what is this point? Oh, this is Mars. No, in Ptolemy model, there is another orbit around this point, and Mars is on that second orbit, which is called epicycle. And later, by times of Copernicus, they added up to 12 or 13 epicycle on epicycle to explain motion. That was very important for astrologists because, you know, the situations when they failed to predict something like solar eclipse and there was bad consequence. And then came Copernicus and put the sun here and Earth and the moon, but still the universe was so small, stars are here. It was worse for astrologists because in Copernicus' theory, the orbits were circular. So they had to wait for Kepler, who said, no, not circles, but ellipses. And then everything became great. And also, of course, Copernicus introduced rotation of the Earth around its rotational axis, which was not here, not existed here. Kepler, Galileo, Newton, Herschel, who plotted this map of the Milky Way. And here there is confusion. Some people think that it's about Milky Way galaxy, like the God's eye view on our spiral galaxy. No, he just looked at the Milky Way that goes through the sky and counted stars and yeah, the shape of the Milky Way on the sky. Nice. These three gentlemen extended the scale of the universe because they measured the distance of stars. Each of them different star. Friedrich Bessel looked at 61st Cygni, which has the biggest proper motion. So he thought it moves a lot on the sky. It means that it is the closest. Henderson, Thomas Henderson, a royal astronomer of Scotland, he traveled to South Africa and he observed, guess what? Alpha Centauri. And he got the distance of Alpha Centauri. And Friedrich Struve in Pulkovo Observatory in St. Petersburg in Russia, he observed Vega in the northern sky. And they three determined, using parallax method, determined distances of stars. So from sphere of stars, which goes immediately after the orbit of the most distant planet, which was at that time Saturn, right? Two distances which are 300,000 times greater than 1 astronomical unit. That's the distance of our of Alpha Centauri. Right, and I should mention that Herschel was the man who discovered the planet. All planets before were known since wherever, since people lived in caves and, you know, didn't know fire or wheel. They could see all planets up to Saturn, but he discovered Uranus. I read somewhere about pronunciation, and it says that professional astronomers always say Uranus. Not professionals say Uranus. So I'm just, you know, I'm professional astronomer. So, and tell me, who are these two people? Okay, their portraits are not popular, but two of them, and that's something very important that has two names, and diagram by, yeah, Hertzsprung and Russell. Yeah, Einar Hertzsprung and Henry Russell. Yeah, they worked, well, published things around this time, so now we call Hertzsprung-Russell diagram. To my students, I say this is heart attack diagram, because Hertz means heart, Sprung means jump. Oh, who is this lady? Henrietta Leavitt. Yes, yes, beautiful young lady. In 1908, she found that Cepheids, I think there were 12 or 13, she found identified in the Large Magellanic Cloud. They show this dependence between period and magnitude. This is for minimum brightness, this is for maximum brightness, so they change their brightness, and the brighter the Cepheid, the greater the period. So in principle, you can determine distances. About Cepheids today, this is Galaxy 5584. I think it is Messier 101. Maybe I'm wrong. Okay, maybe I confused with another object. This is the view of Hubble Space Telescope of the Cepheid, and this is the view of James Webb Telescope. And here are results for two galaxies, this one and this one, and white things with big errors are Hubble Space Telescope. And you see Hubble found 185 Cepheids in one galaxy, and James Webb found 218. And dispersion, the accuracy is much better. You see James Webb red spots, and Hubble very noisy. So we are getting there. We combine this data with data of Gaia, which measures distances using parallax method, and we have nullpunkt, as Germans say, 0 point for Cepheids to calibrate distances very well. Edwin Hubble, Mount Wilson 100-inch telescope. I should say that when I prepared this lecture, I read many his papers. We are so lucky. I don't know if every one of you uses ADS, Astronomical Data System of Harvard University. You can go there, you can write name, years, and you get all publications. Everything is scanned. You just see them as they were published. You can read them. Oh my God, Edwin Hubble was one of the greatest astronomers of, well, all time. And of course, he worked on the biggest 100-inch telescope. This Hubble's law, basically this dependence between distance and velocity, it is 1929. And the story has several dates, and here is very important, 1924, centennial, 100 years now. 18 radial velocities with 24-inch, or should be inch, sorry, Lowell refractor and Lowell observatory. Percival Lowell, who funded and founded this observatory where Pluto was discovered. And maybe you know astronomical sign of Pluto. It has letter P and letter L. Percival Lowell, Pluto. That's why the name of Pluto, proposed by this 12-year-old girl from England, was so well immediately accepted. Because they asked the widow of Percival Lowell, what kind of name would you suggest? And she said, how about Percival? Oh, no, we normally don't do it. How about Lowell? No. And then PL, Pluto, appeared. Great. Okay, so then comes Alexander Friedmann, 22-24. He published 2 papers. He solved Einstein's equations for the whole universe as a whole, cosmology. Hubble 24, great step, demonstrated the most of nebulae are extragalactic. There was a great argument at that time whether they belong to Milky Way or they are far away. He showed that they are far away using the method of determination of distance, and actually showed that we talk about parts of megaparsecs, so maybe more than million parsecs. And 1 parsec is 3.3 light years. So you can multiply and see how much the universe was expanded. From using Herschel-Russell method, from using methods of to determine distance of large and small Magellanic Cloud, it's all tiny here, to other galaxies, to extragalactic scale. Again, I put erroneously, okay, not feet, no, but inches. Yeah. If you have time, look at Hubble 1926 paper, where he summarizes all observations of galaxies at that time. A great paper, 45 pages or something. That's fantastic. Lemaitre, George Lemaitre, Father Lemaitre, 26, also solved Einstein's equation and get a result very similar to Alexander Friedmann, who did it a bit earlier. And then the paper, 1929, Hubble. I want to present a few things of Wester Slipher, who measured spectra of many different objects, planets, comets, stars, nebulae. At that time, as I said, it was argument whether nebulae are galactic or extragalactic. So he just measured everything that he could reach using 24-inch Lowell refractor. Actually, Pluto was discovered on 13-inch telescope in Lowell Observatory. Here he is, Wester Slipher, and look at this. Nebula is photographed. Astronomer detects rotation by continuous exposure. Professor Percival Lowell announced here that Dr. Slipher detected spectrographically rotation in Great Andromeda Nebula. To accomplish this exposure had to be continuous over several nights. And yeah, that's his measurements of galaxies, their redshift, velocity. Most of them go away from us. So since 1918, it was known, this fact, that strangely, looking at spectra of galaxies, they all have a redshift. Doppler effect is applied. It means they all go away from us. And people try to explain it. And of course, naturally, they use solutions of Einstein equation and say, yeah, understood that, yes, there is probably expansion of the universe. Yeah, so it shows how spectral lines shift in the direction of red. If we take object of greater distance. Humason writes, about a year ago, Mr. Hubble suggested that selected list of fainter, more distant extragalactic nebulae be observed to determine, if possible, whether the absorption lines of these objects show large displacement toward longer wavelengths, redshift, as might be expected on the theta theory of curved space-time. During the past year, 2 spectrograms of this object were obtained with Cassegrain spectrograph on 100-inch telescope. The exposure times for the spectrograms were, oh my God, 33 and 45 hours. How did they do it? So there was photographic plate, and then when daytime, what did they do? What was technique? How to screen it from light coming? So it was not easy. And how difficult is this work? Each spectrum required so much effort and time. And then Edwin Hubble, 1929, determination of motion of the sun with respect to extragalactic nebulae involved K term, now we call it H, that Hubble's constant, of several hundred kilometers per second per megaparsec. I add from myself. Explanations of this paradox have been sought in correlation between apparent radial velocities and distances. Already people tried to find correlation, but so far the results were not convincing. The present paper is a re-examination of the question based on only those nebulae distances which are believed to be fairly reliable. So you see, actually there were attempts to explain in terms of expanding universe, but Hubble used the best telescope, the best data, and it was absolutely convincing. That's from this publication. 1 million parsec, 2 million parsec, and velocities. And this is modern data. This data, I think, 2012, using the 6-meter optical telescope in Caucasus. And here is 1 megaparsec, 2, 3 megaparsec. Look at this. They are objects of the local group of galaxies. Actually, all of them are local group. But these objects show both positive and negative velocities. No expansion of the universe, that doesn't effect. But here, boom, 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 they show this effect. 1 megaparsec, 2 megaparsec radius spheres around the Milky Way, about 50 local group galaxies are inside here, inside of 1 megaparsec radius sphere. They are gravitationally bound, do not show expansion. Galaxies outside 1 megaparsec radius circle demonstrate expansion. But I think you all learned and read that expansion of the universe can be seen on the scale of clusters of galaxies. One cluster goes away from another cluster because the fabric of space-time is expanding. But inside of cluster, everything is gravitationally bound and does not follow this general expansion. And scale of clusters of galaxies is like, I don't know, minimum 30 megaparsec, maybe 100 megaparsec. Here we talk about 1, 2, 3 megaparsec, and Hubble also showed the same. And, oh gosh, where am I? No, sorry. I missed some slides, maybe they're later. Basically, what I'm saying, probably later, I had to move them, but I got modern explanation, publications including 2024, is that the general cosmological expansion of the space is one thing. Another thing is the dark energy. The dark energy is everywhere. It is inside me, it is in this room, it is everywhere. And people just calculated, looking at our local group. Supermassive galaxies are Milky Way and M31. And they determine this gravitational attraction of dwarf galaxies around. But there is a dark energy which pulls them to go away from the center, starting from the zero gravity radius, which is about 1 megaparsec. So everything away from 1 megaparsec goes away from the Milky Way and the Andromeda Nebula due to the dark energy. A dark energy acts as anti-gravity here. The general cosmological expansion, this is on huge scale, but dark energy is everywhere. And here people just calculate, knowing lambda term that comes from the cosmic microwave background radiation, and they show that starting from 1 megaparsec radius, expansion due to dark energy is doing this. It's doing this. So, would it be super brave to say that what Edwin Hubble discovered was actually the dark energy? And this is recent publications show this. There is some criticism, but more and more support for this idea. Right. Let me continue the theta. I think it is year 1918, and here is Hubble's law. Here is velocity, down is distance, and r dot over r is Hubble constant. So basically we have, and he writes, he writes here that this solution is given by Dr. George Lemaitre in paper published in 1927. A similar solution was previously given by Alexander Friedmann, 22. So interesting time. And here they are. So who is who? So basically this is priest George Lemaitre from Belgium. This is Alexander Friedmann. This is De Sitter, William De Sitter. Right, maybe I won't explain this. So that's shift of spectral line for more and more distant galaxy. Let's look at it again. Close galaxy, spectral line almost in the right place, shifts, shifts, shifts towards red shift. Remember the previous picture was up to 3 megaparsecs, and if we go further, we come to Virgo cluster, and in cluster everything is plus and minus, you know, positive and negative with respect to the center of this Virgo cluster, all gravitationally bound, and then it goes. Yeah, okay, sorry. Cosmography of the local universe. This is a great paper. And please, there will be something on YouTube or where this lecture? Yeah, and slides. Yeah, please pay attention to this. Here is a great movie of local universe with a great attractor, and they move things in different directions. So you can take a photo of this and find this reference and this paper. Amazing. The movie is a bit slow, so I double the speed like 2 times, and it's just great. We don't have time. The movie lasts for 17 minutes. 2 times higher speed would be like 8 minutes. We don't have this time. So, right. Remapping the close by galaxies. That's again, this is about R with 2 dots is acceleration. And this is due to gravity, and this is due to lambda term, which is the dark energy. That's how people calculate it, and they calculate the 0 radial acceleration surface 1 megaparsec around the center of mass of the system of Milky Way and M31 Andromeda galaxy. That's it. Yeah, 0 radial velocity. Everything goes away due to dark energy. Oops. Due to dark energy, and here normal attraction to this is the Milky Way, and this is the system of Andromeda Nebula, and all together, yeah. Early determinations of Hubble constant. So first gave like 500, 600 kilometers per second per megaparsec. Alan Sandage, who worked with Edwin Hubble, indicated the error in the 0.4 CVs for maximum brightness of stars, and this is a great point. He put 75 kilometers per second per megaparsec. That's basically what we have now. But in his paper, he said that error is 2 times. So can be 75, but can be 150, it can be 30 or something. That's his paper. And you probably heard about the Hubble tension. Planck mission, WMAP, they show the Planck constant of 67 kilometers per second per megaparsec, and this comes from Hubble and Gaia and other techniques, and it gives Hubble constant 73. 67, 73. And errors are small, so really it should be explained. And I found this paper of first DESI result, and DESI is the dark energy spectroscopic instrument in this beautiful telescope at Kitt Peak National Observatory with some very special focal plane. What is great, it can see simultaneously 5,000 galaxies at the same time. So this is to make survey of the universe very quickly, to search for supernovae 1A that shows distances. So basically that's amazing result. Yeah. Okay, and here the results, which are close to results of Planck telescope. Yeah, and here this 73. So this is early universe, and this is late universe. Well, late. Okay, so you can also find this publication and read it carefully. But let me continue. I want to know time. Bill, how much time do I have?
15 minutes.
Oh, you want me to finish at 9? Okay. Yeah, great. So Hubble's law. Oh, well, okay. Right. Sorry, I will jump a little bit. Einstein lived 75, 76 years. I'm not sure, 75 or 76, when he was date of birth, and not too much. In the age of 26, he created special relativity theory, and this is a very interesting situation. Actually, it comes back to laws of electricity and magnetism, and you know all these names, Ampere, Ohm, Gauss, Faraday, and they worked and wrote each of them different laws which are in textbook of physics. And then a genius came, James Clerk Maxwell, and he brought it all together. And he wrote 4 beautiful equations. Actually, later they were changed into 4. Initially, there were more. And in these Maxwell equations, all electromagnetism. In these equations, when you combine them, you get the equation for harmonic oscillations, for waves. And these waves, actually, you can find immediately the speed of these waves. And the speed is 1 divided by square root of 2 constants, which were very well known at that time. Permeability, magnetic permeability of vacuum, and electric. Okay, 2 constants, one from magnetism, another from electricity, and they were known. When he substituted, velocity is equal to 1 divided by square root. 1 constant times another constant equals 2. He calculated. There was no calculator at that time, or Excel. And he got the result, guess what? 300,000 kilometers per second. Speed of light at that time was more or less measured. So, conclusion, there are electromagnetic waves which go with the speed in vacuum 300,000 kilometers. And then started all this story about relativity, about motion. What if the object moves close to speed of light? And another object. And relativity principle of Galileo was changed by Einstein to special relativity principle. This is where this name special relativity comes from. In the same 1905, he explained the photoelectric effect. And yeah, he got the Nobel Prize. NP means Nobel Prize. in 1921 for explanation of the photoelectric effect, because this explanation suggested that there is a quantum, there is a certain discrete value of energy in light, quantum of light, right? And I didn't know that. Actually, I discovered that the term photon for the quantum of electromagnetic radiation for light. The term photon was introduced in 1926, not by Einstein. I don't remember by whom, but you can find. I thought people knew about photons forever. No, it was less than 100 years from now. General relativity, Nobel Prize in 2017, the Penrose black holes. Actually, there were no Nobel Prizes connected with directly with general relativity. Well, from general relativity came the idea of gravitational waves, which Einstein published in 1916. And here is Nobel Prize going to pulsologists, people who study pulsars. And they discovered in 1974 this pulsar, which is binary pulsar. No, not binary pulsar. Yeah, binary neutron star. One of neutron stars. Both are rotating, like lighthouse. One rotates as lighthouse, and we see these flares that come to us, to Earth. And the second rotates, and some extraterrestrials living somewhere else see it as a pulsar. But they are a binary system, and as they rotate around each other, they produce gravitational waves, which, according to Einstein's theory, should lead to degradation. They call it degradation of the orbit. So basically it starts rotating slower, and there are some effects. And look at this. I don't remember whether I've seen ever this theoretical calculation and observational data sitting so well on this. And there is this gap here in observations. Guess why? 1994, they got the Nobel Prize. They started celebrating. That's my explanation. So, right, and LIGO 2017, gravitational waves, got the Nobel Prize. Quantum entanglement, that's famous paper of Einstein, Podolsky, Rosen, 1935, where they said, look, your quantum mechanics is not complete. Look, if we just apply logic, we come to this funny conclusion that you can take two atoms, entangle them, bring one atom somewhere to Alpha Centauri, and then what happened? If you change spin of this atom, the spin of the other changes simultaneously, but the distance is 4 light years. Something wrong with quantum physics. And now we know that everything is fine with quantum physics. Exactly how it happens. And Nobel Prize of 2022 for proof that quantum physics is complete. We have everything that we need for quantum physics, and quantum entanglement now is used in quantum computers. They use Rydberg atoms, easy big atoms, giant atoms, which were discovered in space first, and it's easy to entangle them and get these qubits of quantum computer. Gravitational lensing, and here we are in the mecca of gravitational microlensing. And this telescope we have here, which discovered amazing things. Yeah, and it's also Einstein, 1936, a paper published in Science with the name, title, something like gravitational lensing must exist or something. And he proves it nicely. Okay. Relativity, special relativity. I look at time, 5 minutes. Okay, I skip it. General relativity. Well, basically, in special relativity, he connected space and time in space-time. And he connected matter and energy with this formula. In general relativity, he connected space-time and matter-energy in one equation. Curvature. Even light obeys this curved space. Entire universe in one line, geometry of space-time on the left, distribution of mass and energy on the right. Here is equation from Friedmann. And from this equation, several things follow. This is velocity, this is distance, this is density of matter, and actually velocity divided by distance, it is Hubble constant. And K tells about curvature, and now we know that space is flat, K is equal to 0. Critical density follows from this equation, 10 to the minus 26. 6 hydrogen atoms in 1 cubic meter should be in the universe, according to Hubble constant. You see, that's one constant that we measure. All the rest we know. Gravitational constant, pi, we know everything. So we can determine it. Critical density. So if density measured is greater, then the universe should expand and then collapse. If density is less than critical, it will expand forever, and so on. So that's what two teams who studied supernovae 1A in the United States and in Australia. Brian Schmidt was here and gave talk, a Nobel Prize for discovery of the dark energy. They thought that they would see probably the curvature going like this, or maybe like this, or maybe like this, and they would determine this K, the curvature of space. No, but the result was going up, expansion with acceleration, the dark energy, anti-gravity. Right. The origin of elements. I should mention about it. I have 2 minutes. George Gamow, fantastic guy. He initiated and did the most of this fantastic paper. Alpha was his PhD student, but he always joked. He wrote funny books and so on, and he invited his colleague Hans Bethe to be a co-author. And since then, everyone calls this fundamental paper Alpha, Beta, Gamma paper. They just calculated that there should be, if the universe expanded from super hot stage, there should be 25% of helium. Yeah, so that's how it happened. So time at the moment of about 3 minutes, this amount of helium was formed, this amount of deuterium, helium-3, tritium, beryllium, lithium, 5, 6, and 7. And this is what we see now. Here is the parameter. Density of baryons. Baryons are neutrons and protons, just normal atoms, divided by critical density. And here we come to this number, less than 0.1. Not critical density, but very small. But remember, there is dark matter, discovered first by Fritz Zwicky in 1933, the father of the dark matter. And then the mother of the dark matter, Rubin, what's her name? Huh? Yeah, Vera Rubin, yes. The mother of the dark matter, she discovered it in rotation of galaxies. So with the dark matter and dark energy, we would have this. So this amount comes from CMB, and this is amount of helium, deuterium, very exactly determined, helium, 3, lithium, amazing. So some people say, can the dark matter be made of baryons? Maybe it can be gas, a lot of gas that we don't see. Maybe they can be brown dwarfs, which we cannot see, a lot of brown dwarfs. Maybe they can be black holes, which used to be baryonic matter before collapse. No, the vertical line would have to move to the right, to this position, if the dark matter was due to baryons made of brown dwarfs or black holes and so on. No way, dark matter should be made of whatever, but not normal protons and neutrons. Gamow predicted the cosmic microwave background radiation, and that's quotation from him. He calculated the temperature should be 5 degrees Kelvin. In fact, we know now it is 2.7 degrees Kelvin, temperature of cosmic microwave background radiation. And he said, can we observe this radiation? And these two engineers, Bob Wilson and Anna Penzias, working in Bell Lab, discovered cosmic microwave background radiation with this antenna. And there is a lot of anecdotes about it. Right, I skip this. Cosmic microwave background radiation, great mission boomerang, actually. In using these winds they blow in Antarctica, they started this they started this balloon in one place, and after it got all around Antarctica, they caught it, and there was telescope there, and the conclusion was the universe is flat. And this is what? My last slide. Outstanding questions. What is the dark energy? We don't know. What is the dark matter? We don't know. There is a problem of antimatter. We don't understand why in the moment when antiparticles and particles had to annihilate together, they didn't annihilate all of them. Actually, 1 out of 10 billion particles survived. Why there is such 1 out of 10 billion asymmetry? So now we have 10 billion photons of this cosmic microwave background radiation per 1 baryon in the universe. So they annihilated, but not completely. And thanks to this not complete annihilation, we are here. You probably read this. Along with antimatter, the dark matter, we recently discovered the existence of doesn't matter, which appear have no effect on the universe whatsoever. That's probably my last slide before the thank you slide. Cyclic cosmology. Convolution? No. Okay, Roger Penrose, CCC, conformal cyclic cosmology. And that's very interesting to find his lectures in YouTube and listen. Roger Penrose, laureate of Nobel Prize for black holes. Thank you. Thank you.
Was everything known about the universe in just over an hour? I can't get that anywhere else. Questions for Sergey?
Sorry, please. Just one, with limited knowledge. The 1 megaparsec limit, right, for expansion of matter outside of
from the center.
Does that apply no matter the mass, the size of the system?
No. It is calculated exactly for the density of dark energy, which comes from Planck mission and so on.
Right.
We know the density. It comes from the mass of Milky Way galaxy and Andromeda galaxy in the center.
Right.
And we just have equation. And from this equation, we find this zero gravity radius.
So that model fits
inside gravity, outside anti-gravity, dark matter, dark energy.
Beyond those two.
Beyond, there are other clusters and groups. And actually, I had no time, but it reminds me the tides, oceanic tides. So when you explain the theory of tides, there should be like tides going around the Earth as the moon goes around the Earth, and they follow the moon, well, a little bit of the sun. But when they meet the landmass, like New Zealand, look at animation of tides around New Zealand. That's amazing, all these streams and so on. So this is what's happening around these local groups. But this conclusion that Edwin Hubble discovered the dark energy, I think that's amazing. But I would put still a little question mark. Yeah.
I guess that 1 megaparsec would be different for other galaxy clusters.
Yeah.
Virgo cluster would be different.
Absolutely, yes. And there was a recent paper which did the same work for Virgo cluster, and they found similar effect. But remember, I told you, take a photo of this and look at these motions, and you will see the great attractor and other beautiful things in local universe.
Thank you.
Yes?
I think the answer to this question, you might have skipped over one of your slides, but when we see the cosmic micro background, why do we not see anything after that? Or do we? And we just...
Okay. It's like, I had this slide, but I skipped it. Like the guy is standing here looking at clouds. He can see things before clouds, but not inside clouds, because this is the line of the last scattering of light in this media. And in this case, the media is plasma of early universe. And photons cannot leave this plasma. They're entangled. They are, coupled. After that, photons fly freely towards us, and we get it.
But so we get it all the time?
All the time, yeah.
So I think I've asked the question before.
Okay.
The cosmic micro background is effectively as far away and as far back in time as we can see. It's the oldest light.
Okay. So, cosmic microwave background, that point, so to say, it doesn't exist anymore. Now the universe is very dull. It's very dark. The whole universe is very dark. We see it bright as a firewall around us everywhere, because astronomy is time machine. We see back in time as we see farther in space. But the universe today is as it is close to us.
Yeah, but
Yeah.
if you think of stars and galaxies that formed after that, we can tell how far away they are,
Yes.
how far back in time they are.
Yeah.
But is there a cosmic microwave radiation that's younger?
That
That is younger than the farthest back. Because presumably as the universe cooled down, it's still
Okay.
radiating lots of
Yeah. I can just repeat that light couldn't leave plasma of early universe. Younger light was there, but it cannot come to us. And we can continue this discussion later.
Okay, have we got any more questions for Sergey?
That's very, very active three gentlemen. Yeah, no, please.
There's somebody over there.
Okay. So the question you just touched on just earlier on when you got particles that have been linked, quantum particles. So entangled. So we've thrown out hidden variables. That works now being kind of Einstein's EPR and hidden variables. So we now know that these particles that are entangled, that are in supersymmetry, break this symmetry instantaneously, and they appear to do so faster than the speed of light, as we observe. What is the thinking on the mechanism right now? Because clearly that appears to contradict.
Right. Okay. I would be careful using words. I would be careful using words symmetry and supersymmetry. This is about something else. But in quantum physics, we have this rule. When you explain something, the student starts asking question, we answer, another question, answer, and then we say, shut up and calculate. Because quantum physics, I don't think anyone understands it fully. There are interpretations, there are opinions, but probably no full understanding.
But
the
action is as they are the same thing, although they are apart. The action.
Okay.
Well,
Calculate.
So we've got supper down in the Matariki room. It's got its ready for us. So thanks again, Sergey, for.
Thank you very much. Thank you. Thank you.